Here is a function. It is called x squared times sine of 1 over x. And near 0, it does something strange. Watch what happens when we zoom in. More wiggles. Zoom again, even more. This curve crosses the x-axis infinitely many times, in a space smaller than a grain of sand. So what does this function approach as x goes to 0? Substituting doesn't work. You'd be dividing by 0 inside the sign. A table of values doesn't work. The numbers jump around. Factoring doesn't work. There is nothing to cancel. But there is a method that answers this in one line. It doesn't study the function at all. Forget maths for 20 seconds. Imagine 3 friends walking down a corridor. The one in the middle is blindfolded, and the other 2 are holding her hands, one on each side. Now suppose I tell you that the friend on the left ends up at the blue door, and the friend on the right also ends up at the blue door. Where does the blindfolded one end up? You already know. She has no choice. She ends up at the blue door too, and you never had to watch her walk. That is the entire theorem. If a function is trapped between 2 other functions, and those 2 head for the same number, the trapped function is forced to that same number. We never need its formula. We never need to be clever. We only need the trap. You will hear it called 3 names. The Squeeze Theorem, the Sandwich Theorem, and in older books, the Pinching Theorem. Same idea every time. Something in the middle, with nowhere to run. This trick is not modern. Around 250 years before the Common Era, Archimedes wanted to know the value of pi. He could not measure a circle. He drew a polygon inside the circle, and a polygon outside it and squeezed. His answer: pi is bigger than 3 and 10^71, and smaller than 3 and 1/7. He never found pi. He simply refused to let it escape. That is a squeeze, 22 centuries early. Here is the statement properly. Suppose that for every x near a, but not necessarily at o itself, g of x is less than or equal to f of x, which is less than or equal to h of x. Suppose also that the limit of g as x goes to a equals L, and the limit of h as x goes to a also equals L. Then the limit of f as x goes to a must equal L. 2 pieces of fine print, and they are where marks get lost. First, the sandwich only has to hold near a, not everywhere. The curves can cross, tangle, and misbehave far away, and the theorem does not care. Second, and this one is fatal, the 2 outer limits must be the same number. Watch what happens if they aren't. Here the lower bound goes to 2, and the upper bound goes to 5. The middle function can now oscillate forever between them and never settle. The trap has a hole in it. One more thing the theorem never asks about: the value of f at itself. It can be anything. It can be undefined. A limit is about the journey, not the destination, and the squeeze respects that completely. Let's prove it. And I promise the proof is just the picture, written down. First, what does a limit actually mean? It means this. You challenge me with a horizontal band around L, as thin as you like. I have to find a window around A, so narrow that inside it, the curve never leaves your band. Now the proofs. Someone hands us an epsilon. Because g goes to L, there is a window, call its width delta 1, where g is above L minus epsilon. Because h goes to L, there is a second window, delta 2, where h is below L plus epsilon. And there is a third window, delta 3, where the sandwich inequality actually holds. Here is the whole trick. Take the smallest of those 3 windows. Inside it, all 3 facts are true at once. So L minus epsilon is less than g of x, which is less than or equal to f of x, which is less than or equal to h of x, which is less than L plus epsilon. Chop out the middle and read the ends. F of x is squeezed between L minus epsilon and L plus epsilon, which is exactly the statement that f of x minus L is smaller than epsilon. We answered the challenge. The limit is L, done. Back to the monster from the opening. The key is a fact you already know, and it is the most useful fact in this entire topic. Sine of anything at all is between -1 and 1. Always. No exceptions. So -1 is less than or equal to sine of 1 over x, which is less than or equal to 1. Now multiply all 3 parts by x squared. And notice something important. X squared is never negative, so the inequalities keep pointing the same way. Multiplying by a negative would have flipped them. Finally, as x goes to 0, negative x squared goes to 0, and x squared goes to 0. Same number, both sides. So the wild function is squeezed to 0. One line, no cleverness, and the monster is solved. Now the limit this theorem exists for. The limit of sine x over x, as x goes to 0. Substitute and you get 0 over 0, meaningless. Yet this limit is the foundation of all trigonometric calculus. Without it, the derivative of sine does not exist. The proof is geometric, and it is beautiful. Draw a circle of radius 1. Mark an angle x, measured in radians, and keep it between 0 and 90 degrees for now. Now look at 3 regions that all share the same corner. The small triangle has area 1/2 sine x. The pie slice has area 1/2 x. The big triangle has area 1/2 tangent x. And look, the small triangle sits inside the slice, and the slice sits inside the big triangle. Nested regions mean ordered areas. Multiply everything by 2. Then divide everything by sine x, which is positive here, so the directions hold. That gives 1 less than x over sine x, less than 1 over cosine x. Now flip all 3 fractions upside down. Flipping positive numbers reverses the order, and we land exactly where we want to be. And there is our sandwich. Cosine x on the bottom, 1 on the top, and sine x over x trapped in between. As x goes to 0, cosine x goes to 1. And 1, obviously, goes to 1. Both sides arrive at the same number, so the limit of sine x over x is 1. Why does this matter so much? Because when you work out the derivative of sine from first principles, this exact limit appears, and it collapses to 1. That is the only reason the derivative of sine is cosine. Every trigonometric derivative you will ever write rests on a squeeze. The squeeze is not limited to functions. It works on sequences too. Take sine of n over n, where n counts up through the whole numbers. Sine of n bounces around unpredictably forever, but its size never exceeds 1. So the whole thing is trapped between -1 over n and 1 over n, and both of those collapse to 0. Here is a favorite. What is the nth root of 2 to the n plus 3 to the n, as n gets huge? Notice that 2 to the n plus 3 to the n is at least 3 to the n, and at most twice 3 to the n. Take nth roots of all 3, and the answer falls out, 3. It works out at infinity as well. What does x plus sine x over x approach as x runs off to infinity? The sign wiggles forever, but it is bounded, and dividing by an exploding x crushes it. The answer is simply 1. And this is not just exam maths. An engineer who cannot compute a value exactly will bound it from both sides and tighten until the bounds meet. A computer scientist proves an algorithm's running time by squeezing it between a best case and a worst case. A physicist brackets a messy measurement between 2 clean ones. Trapping is often easier than solving, and sometimes it is the only option. 4 mistakes to avoid. 1. Bounds that go to different numbers prove nothing at all. 2. Multiplying an inequality by something negative flips it, so if your multiplier could be negative, use its absolute value instead. 3. You only need the inequality near a, so don't waste time proving it everywhere. 4. Your bounds must be functions, whose limits you can actually find. Squeezing with something as hard as the original gets you nowhere. And the recipe which fits on a napkin. Step 1. Find a bound, almost always by starting from sine or cosine being between -1 and 1. Step 2. Check that both bounds go to the same limit. Step 3. State the conclusion. 3 steps, and some of the hardest limits in calculus fall over. Your turn. 2 problems. 1. The limit of x squared times cosine of 5 over x, as x goes to 0. 2. The limit of sine n over n squared, as n goes to infinity. Both are 1 line each. Put your answers in the comments. And if the sandwich finally makes sense, subscribe, because next time we are taking this idea further.